Hello everyone. The topic of today's lecture is Paxos quorum leases. The lecture is prepared for CSCI 4160. What's Paxos? Paxos is a distributed algorithm for reaching consensus between replicas. And on the slide, you can see the name of the paper where Paxos was firstly introduced. And the second is the link to the video prepared by site reliability engineer from Google with the detailed explanation and examples of Paxos algorithm. The Paxos algorithm was the foundation for many distributed algorithms and has a lot of modifications. Why change Paxos? Why Paxos wasn't enough? So Paxos itself is quite expensive algorithm, and if we analyze the system where the distributed algorithm is used, we can come up with the modifications that improve the performance. So, for example, average user on social media, if we compare the number of posts he reads and the posts he writes a day, we know that the number of posts he reads is much more than he writes. Or another example that will be more familiar for CSCI students is the Piazza posts. And we can see that the number of views on this post is 36. So we can see that one write corresponds to 36 reads. And knowing that read requests are much more dominant than write requests, we may modify Paxos and improve the performance of the read requests. So before that, let's know what the lease is. So lease is a time-limited promise from one process to another to not modify an object during the lease duration. So how can we use this? What's the application of this promise? So we know that if promise is given and promise is held, we know that the data on the data wasn't changed, and which means that replica that knows that data wasn't changed knows that the data on this replica is the actual data. Therefore, this replica can consistently serve the read requests by the different users during the period of the promise. So, if replica during the promise can serve the read request locally, what advantage it gives us? So first of all, it improves the throughput of the read requests, since all of them handled locally on the replicas, and since all of them are handled locally, it also improves the throughput of the write requests. And the most common application of the leases is in multi-Paxos environment, when a leader handles all read requests. Another approach used in several Google applications is to allow all replicas response user read requests locally. But if we allow all replicas response to users, we need to make sure that all the replicas are consistent, which brings the overhead to make sure that all replicas are consistent, and it will slow the write requests. And the solution we want to use and explain in this lecture lies in between, and it's called the quorum leases. And quorum leases is a model in which leases are granted to different subsets of nodes. Leases are already promise given from one process to another to not modify only some part of the data, and having knowledge about the behavior of the users, especially when we know that our replicas are located in different parts of the globe. For example, one can be in New York, one can be in Hong Kong, one can be in India. We know that users in these regions are active at some point of time. For example, usually users are not active during, like, for example, from 3 a.m. till 6 a.m. But are much more active during the evening time, like from 6 p.m. till 8 p.m. Also, having in mind the location of the replicas, we may use this and select different subsets to provide leases, to grant leases, and therefore improve the performance of the algorithm. Now, as we got a basic idea of how it works, let's go through the intuition and the revoke mechanism. And after that, we'll ask some important questions about the implementation part. So, what is revoke mechanism? For example, when some process grant lease to another process, and assume like process on the left grant lease to the process on the right, and left process after some period of time in the middle of the expiration period wants to change the object. If it wants to change the object, it sends the revoke message to the process on the right, and after that, process on the right knows that the object will be changed, and therefore it stops local reads. Local reads are not allowed anymore, and it sends the OK message to the process on the left. This is the case if the lease was revoked. In case of the expiration, we see that it's the same situation, but after a period of time, lease expires and local reads are not allowed anymore, and local writes are not possible. And in the period before the lease expired, we see that users can read from the replica on the right, and users didn't write to the replica on the left. So assume the situation that we know that in Paxos algorithm we need receive acknowledgement from majority of the nodes in order to commit command. So assume that we give the majority we grant leases, and therefore in order to receive acknowledgement from this majority, we need to send the revoke message and receive OK message. And if some machine in the quorum, in the lease quorum is not responding, it means that command will not be committed, and therefore whole machine works until lease expires, which brings the first question: how to choose the expiration period? Because if the period is too long, it means that it is possible that when some node wants to commit the data, it may wait too long. But if the expiration period is too short, it means that the period during the time when local reads possible, it's very short, and it means that the performance improvement that we get is short and not significant. And another question to ask is how to choose replicas for this. We know that, as I said before, that replicas are located geographically in different places, and therefore we need to, replicas can be selected in the way where some certain objects will be accessed more and read more, rather than in another replicas. For example, assume we have a government election in Hong Kong, and therefore we have two different replicas. One located in New York and another located in Hong Kong. And the election results are coming out in some government website, and people want to know the results. And therefore, it can be clearly be deduced that reads from this website reads the results of the election will be much more in the Hong Kong replica rather than in New York replica. So in this way, this is the example how we can choose the replicas for these and which objects to use. So let's look on the definition of the complete definition of the promise. So a replica G grants a list to a replica R on a set of objects O by making a promise. The first part of the promise: notify R synchronously before committing any update to any object in O that G proposes. So in other words, we want to make sure that if replica G granted list to a replica R, so if G receives write command, synchronously R will receive the message and stop serving the read request locally. And the second part of the promise is to acknowledge. So first part is for proposers in original access algorithm, and the second part that receive propose from proposer. So the acknowledge, accept, and prepare messages. This is messages from original access algorithm for updates to objects in O, only with the conditions that the proposer must also notify R synchronously before committing these updates. This one is for to make sure that if there is a possibility that some nodes may not know about the promises granted from different nodes to other nodes, and by this message, the node that wasn't aware of this grant will know. So how to enter the first part of the promise? First part of the promise is simply achieved by making the so when the node wants to commit write command, it should have a majority acknowledgement, and all acknowledgements should be from the leaseholders. It means if J granted a lease to several replicas, this node should receive, before committing the write command, it should receive OK message, OK response for revoke message from all of these nodes. And the second is simply achieved as similar with the raft algorithm by using piggybacks. So when proposer sends a message to a node that he wants to commit some command, the node that granted at least several replicas will send the response message and attach the ID of these replicas. Another rule for quorum list is the list becomes active only after a majority of replicas have granted the list to at least one holder. We know that at some point the promises may be revoked, and therefore a leaseholder has when leaseholder has fewer than majority valid promises from different replicas, the lease is said to be inactive for that holder, which means that this node cannot assert the read requests anymore to make sure that everything is consistent. So another question that we discussed before is we know that some nodes will be accessed more on some objects and some nodes will be accessed less on some objects. The example that I provide about the government selection in different regions, and therefore at some point of time we want to change the set of objects and set of replicas. Now if we think how can we come up with a solution to formulate the algorithm, how to achieve the approach to use to achieve the communication between the replicas about the changing in sets of lists and objects. And this done is similarly as Pax's algorithm for the messages, when a node send a message and expect to receive the response. Let's go through this approach. So how this communication is achieved? There are two types of messages apart from the original Pax's algorithm messages. The first type of messages is for agreeing on these configuration changes, which the messages that determine the set of forms and the set of objects. And the second type of messages is for granting and reflection leases. So the natural question can be asked, why keep them separate? Why we can use one type of message and pass the data about both of them? So the answer is we want to keep them separate because there are two advantages of that. The first advantage is we know that replica spread are globally spread, and therefore the hardware can change, the connection between replicas may change, and we want to independently change the granting protocol to make sure that everything works for our needs. In other words, we want to change the granting protocol for form leases, and this change will not affect the other messages. And the second reason is to keep these expiration periods short. So how it keeps this expiration period short? Since the granting protocol messages will be easy and in terms of the number of messages are not expensive, we can make the periods shorter. And why we need the shorter period of expiration? As I said before, when G grants a list to R, if G receives write request, it will first asynchronously notify R and wait for R response. And if R is not available anymore and not responding, then G should wait the expiration time of this list, and therefore it will hurt the availability. Having simple granting protocol, we can make the expiration period shorter and keep them shorter. And
so until now, I think you guys have some concept in mind how the list configuration is going on. So I think you will know that the list configuration is doing through the Python system. So every replica will have its own version of the configuration. Someone is older, someone is newer. Yeah, and okay. Now we're gonna talk about, if you know that, we're gonna talk about how we activate the list. First, every replica will send a promise to every other replica in the system. This means that replica want to be a guarantor of the replica that they send a promise to. If the promise will include the configuration number, like how the configuration that they have, is it new, is it old, something like that, the list duration and the timestamp. When a receiver got the promise from a grantor, if the version of the configuration is older than the one that the receiver have, it will reject the reject that promise. So this picture will explain how the promise system is going on. Like R1 want to send a message, want to send a promise to the R2. This means that R1 want to be a grantor of the list that R2 holder. So first, R1 will send a GAP message to R2, and after R2 got the GAP message, it will start counting the GAP time and will reply back to the GAP message. And after R1 got the reply, it will start counting the GAP time. This GAP time and this GAP time is the same one, like it had the same duration. And after we start counting the GAP time, we will send a promise to the R2. And yeah, after R2 got the promise, it will start counting the list time and reply the promise back to R1. After it reply, start get the reply from R2, it will stop counting the GAP time here and start the list time here. So in this picture, we will know that from T3 to here is a duration that R1 or Genter cannot update the objects, and the duration from T4 here to here is the duration that R2 can read the object locally. So my question is, what happened if R1 didn't got the reply for the promise message in the GAP duration here? So that can will be happening on this one. So if it don't got a reply here, after the ending of the GAP time, it will start counting the list time immediately. And yeah, and this period is a period that they will not update the object without letting the R2 know. So why we have to do like this? This may be a case that R2 got the reply, got a promise, and like start the list time here. It means that if we read locally in R2, read it objects locally, if R1 like don't got the reply and think R2 is dead, and it just start counting the time here. So it means that in this period of time around here, R1 can apply any update on the objects, and R2 we don't know that. Maybe R2 we don't know that. And yeah, so maybe R2 will read the data in the object, and but I don't know that it's have updates. So to make sure that the period here will cover all the period here, so we have to start counting the list time after we ending the GAP time, even we didn't have a reply back. So yeah, after we end the list duration this time here, we want to renew the promise to keep the R2 read the objects locally. So we want to like renew the promise again and again. But the next time that we renew the promise, we will not send the GAP message anymore. because we will act the last promise as a get message. So for this example, we have a get message here, and we start the promise here, and we end the promise. We end the list duration, and we want to send the promise again. So we will use this one as a get message, and you will send the promise here. And yeah, after you send the promise, it means that you start counting the get message again, the get time again, and everything will go through with the same logic. Yes, for the new one, yeah. And if we repeat this and repeat again and again. So the next part, after you receive a promise from author Lepica, it means that uh the list holder will consider the list activate when only we got the like half of the promise from author Lepica. Like in this example, we have a 5 replica. So mean that at least you want to replica, you want to permit from auto replica from your peer. So that is not equals. So yeah, so we see that R1 got 3 promise, R2 got 2 promise, R3 got 1 promise, R4 got 2 promise, R5 got 1 promise. That is not expert yet. So in this case, R1, R2, and R4 will activate the list, but R3 and R5 won't activate the list because half of the peer is 2, right? So unless you want to promise from your peers to activate your list. Yes. So we know that in person and multi-person, they're holding a strong consistency. It means that all the operation are strictly theorizable. So in this section, I will show you that the column list also holding that ability. It means that it's holding a consistency guarantee. So in the computer, we have 3 types of operation: the write only operation, read write operation, and read only operation. So the first 2 types of operation, write only and read write operation, will be committed through the action system. But the special one is a read only operation because we had a period of time that some replica can read the data locally. So the read only operation will be either be served locally by some replica or it will send through the person. So how we decide which read operation to lead locally or send through the person? Okay, let's see the next picture. So we have 3 replica, replica 1, 2, and 3. So and replica 1 holding the A and B object A and object B that's still active, and R2 holding C and R3 holding ABC. So if we got a operation that want to get the value of A to here, so R1 will reply the operation because it have a holding a list on A object, so it can read it locally. So it's equal. It means that we don't have to send this operation to the person. We just like reply it locally. So the next thing is we want to read A and C. This means that, but I want only have A and B. So but due to they know the configuration of the system, so they know that R3 can provide. It will send the operation to R3 and yeah, it will read in the R3 locally. What about if R1 have a operation that want to read D, which is no one holding the D object, right? So if no one holding that object and can read the object locally, it will send that operation to the person system. Yeah, that is how we decide which read-only operation will send to the pixel or not. So that is about the operation read-only. So the next part that, so how we can guarantee the consistency. So for the special one is a read-only operation, right? Yeah. So we have two cases, everything to the person, so that ensure the consistency because the person protocol is ensure the consistency. But if it serviced locally, how we ensure this? So we have two cases that we have to consider. The first one is we have a read operation that finished before the write operation begin. And the second one is the write operation was committed before the read operation begin. So for the first case, we will show from this example. First, we have x equal to 5, and then we read x, and then we write x equal to 2 here. So in this case, when you read it, we got 5, right? Because we read it before we change it. The second case, for the second case, we can divide it into two cases. The first case is the reader have a list before the write operation begin. The reader term here is mean that the replica that apply the read operation locally. So we will show is from this example. The example here is we have R4 is a holder of the object A, and we have this R4, the holder here have promise from half of the replica because it's active. Okay, so and one of that grantor is 3. So and yeah, and R1 want to propose the right operation A equal to 2 here. And you send the operation to half of the replicas, so it's into at least 2. And because the grantor is half of the replica, and the R1 send the message to half of the replica, so it means that we will have one replica that is a grantor and also got the message here. So yeah, that in this case is R3. So R3 will let the proposer index R1 know that, oh, we have someone that holds this object. You have to notice him. So yeah, R1 have to notify the R4 that I have some update on your object. So and R4 will reply it back here. And after and only after R1 got the reply, they can commit that command. That is how we ensure the consistency. So, but we don't want to do the additional communication here. We want to do only like the normal person here. So the solution of this thing is because we know the configuration of the list, so R1 can know that who is holder the A object, and they will let that guy be a one that like send the message to. So in this case, R3 holding the holder is a holder of object A. So R1 send a message to R3, and yeah, it's committed in here easily. Don't have to do any additional communication here. So that is better than the first one. So the next case is the reader didn't have active the list before the write operation begin. So in this case is also divided into 3 cases. The first one is the reader is a one of the we come to these cases first. The reader be the acceptor of the write operation. So it means that like in the system we have the reader that have to send a message to half of the replica to like before it commit the message. That is a normal person, and one of them is the reader R. So the reader R will know the right operation here before they read the the value of A. So it must execute read operation before write operation. The next case is they exist some acceptor of the write operation that also be a grantor of the object. So this cases will be the same with the case that we're talking before here. So here, like this, the acceptor, they are the acceptor that also be a grantor. So here, the acceptor here also be a grantor. So this case is the same with the first one. The last case is they have some acceptor that first we accept the bill first, and then become a proposer promise after we like accept the right operation. So we show this. So this is a 5 replica here, and R3 is a holder and want to read the data, and R2 is a grantor that accept the right operation. After the accept the right operation, the orange one here is a right operation. This is log entry, and the orange one is the right operation. So after R2 accept the bill and they send the permit to the R3, so R3 have to apply the log until is like is to here to like the R2 before it can read locally. So mean that R3 will be the same as R2 now before it can read locally. It means that you apply the yellow log entry here. So it means that it will execute the write operation before read operation. That is mean that, yeah, that's the end of this case. So for now, we ensure that the consistency of the system is correct. It means that we have a serious ability here. So the next thing is how we handle when some replica is dead and drop. So the only way that we can detect the replica is dropped is they not reply the message. Like they don't have the reply to promise message, or they don't have a heartbeat message to alter replica. So after someone noticed that one replica is dead, they will send the message, the special message to the reader to change the list configuration, and the reader will propose the new configuration to every replica, and yeah, and every replica will apply for that new configuration after they end the list duration. I mean the list and delete duration. That is all about here.
If you have any question regarding this presentation, we'll be happy to answer. You can send these questions on the following emails. Thank you very much for your attention.